So this is going to be the final lecture of the course. This is lecture 16. And the title of this lecture is The Search for Life. And so what we're going to be talking about is how do we go about actually looking for life, evidence for life beyond the solar system. So, we've talked quite a bit about, where life might be within the solar system. And remember, we emphasized that some of the best places for life in the solar system might actually be beneath ice sheets around these icy moons, or around some of the giant planets. Now, looking for life there is going to require us actually physically sending probes there and trying to find evidence for it. But, as this picture sort of is supposed to emphasize, most of the chances for life beyond the Earth are not within the solar system. Okay, every one of these dots is basically its own solar system with planets. And so how do we go about searching for life in the broader galaxy, given how far away the stars are? How do we go about doing that? So, let me emphasize again, and we talked about this last time, that something like 20% of all the stars in our galaxy have planets that are Earth-like in the sense that they're rocky and small, okay, so they have perhaps solid surfaces, and they're in their habitable zones. So if they have the right kind of atmospheres, they could, in fact, have liquid water. Okay, this is a huge deal, right? 20% is a big percent, especially when you're talking about hundreds of millions of stars. Okay, so you're sort of in the tens of billions of potentially habitable planets that might exist out there, right? Keep in mind, too, that this is a very recent discovery. So I've emphasized this before, but if I were giving this lecture 2 years ago at this time, I could not have said this. Okay, so this is new stuff, and we're still trying to kind of grapple with what are we going to do with this number. But the big picture is, right, is that if life is common, okay, if life is common in the universe and it's common on these planets, that's a lot of chances. And there's a real chance that in your lifetime we'll discover that it's there. And so what I want to talk to you about is how we would go about discovering it. Now, when I say life, okay, I'm just meaning life in the very specific sense of something that's alive. So I'm really thinking probably most likely microbial life, or maybe something more like plant life, something along those lines. I'm not necessarily meaning ET or some kind of extraterrestrial intelligence that we're going to have a conversation with. It's really talking about the kind of life that existed on this planet for the bulk of its history, and not the kind of life that's only existed for the last blink of an eye, which is basically us. At the end of this lecture, I will begin to talk about the search for extraterrestrial intelligence and how we're going about doing that. Okay. So a good way to start thinking about how you might study a planet that's like the Earth, that's beyond the solar system, is to think about what the Earth looks like from afar. And as I talked about last time, right, the Earth is incredibly dim. Okay, it's 1/1 billionth as bright as the sun. So if you're trying to look, just blindly look at the Earth, it's a hard thing to see without working pretty hard to do it. I'm just sort of showing this picture because it's cool looking, and it sort of emphasizes just how sort of small in the scheme of things the Earth really is. This is taken by the Cassini spacecraft, and this is a picture of Saturn. Okay, so it's out there near Saturn, taking an image of Saturn. And this little box right here has been blown up in the corner. And so let me, I don't know why these are all, it's dark enough. This box has been blown up here in the corner, and that little teeny dot there, that's the Earth. Okay, so that's what the Earth looks like, not even in the glare of the sun, just seen from a distance of Saturn. Okay, so it is a teeny tiny, what Carl Sagan called pale blue dot. And so this is what we're thinking about trying to study around distant stars. However, in principle, there's actually quite a bit we can learn if we could really get at the light that's either reflecting off this distant Earth or perhaps light from the star that's shining through the atmosphere of this distant Earth. So for example, you might look for direct indications of liquid water on the planet, and you might see this by, for example, water vapor. If you see water vapor on a planet and you have some sense of what the temperature of the planet is, you can get a sense that, well, some of that water might not be vapor, it might actually be liquid. So how would you go about looking for these kinds of things? Well, the way you can do it is via spectroscopy. Okay? It's the same method that I talked about using to determine what the composition of stars are. Okay, so it's this idea of you have light. Light is shining through a gas of some kind, and the gas preferentially absorbs certain wavelengths of the light. And the wavelengths of the light that are absorbed by this gas depend on the nature of the gas. So if you can measure what's called the absorption spectrum, or the spectrum of light, that's coming through, that's shining through an atmosphere of a distant planet, for example, you can hope to figure out the molecular content of that atmosphere. You can figure out whether it's got carbon dioxide or methane or oxygen or whatever. And in fact, this is how we basically first knew the makeup of Venus and the makeup of Mars. It was sort of via spectroscopic observations. It's how we knew what the atmospheres of these planets were like. Okay, so it's this kind of thing. And so what can we look for? In addition to water vapor, we could look for ozone, okay, O3. Ozone is a really interesting signature in the atmosphere of the Earth because, first of all, it tells us that there's oxygen there. But even more importantly, if you just killed all the plants on Earth, okay, if you killed all the photosynthesis on Earth and had them stop producing oxygen, the oxygen in the atmosphere of the Earth would not last very long. It would be in an unstable situation. It would get absorbed up, binding with other things on the Earth and in the atmosphere, and it would be gone in short order. So if you look at a system like the Earth and you see the presence of ozone, you know something funny is going on. There's something is producing that oxygen sort of out of equilibrium from what you might expect it to be. Okay, so ozone in our Earth is a telltale sign that something funky is going on our planet, that there's some life that's producing this stuff. Another gas in our atmosphere is methane. And a lot of the methane in the atmosphere of the Earth is produced from, living organisms, right? It's why cows are stinky. It's all the methane they produce. So if you see methane in the atmosphere of the Earth, it's not the only possibility, but if you see methane, that might be a signature for life. Etc. And so the idea is you have some black body spectrum of light that's shining through the atmosphere of this star, this planet, and you see dips and features in that spectrum, and those dips and features tell you, oh, there's carbon dioxide, there's ozone, there's water. So we see this stuff there. Now, if you look at a spectrum of the Earth, so this is an example now, what would the Earth look like if you were just seeing it from afar? There's sort of two components, okay? So first of all, if you're looking at the Earth from afar, the Earth is very, very faint compared to the sun, okay? So here's the spectrum of the sun, okay? This is wavelength of light. It's got cut off, but you think this is just specific wavelength of the light. And this is just how much light's coming out at each wavelength, okay? And so this is sort of the black body spectrum of the sun here, okay? And if you look at the light that's coming off the Earth, that's reflected off the Earth, so the sun shines on the Earth and then it gets reflected back out into space. If you study that light that's reflecting off the Earth, what do you see? Well, you see one bump that's basically reflected light from the sun, okay? That's what this is. Notice how much dimmer it is than the sun. This is this factor of 1 billion that we talked about. It's 1 billion times dimmer than the light coming out of the sun. But then there's this other bump here, and this is the thermal piece. So this is the fact that the Earth has a temperature, and so it's also glowing. So it has its own little black body curve right here, okay? Now in the thermal spectrum, at this wavelength, these longer infrared wavelengths, it's actually not 1 billion times dimmer than the sun. It's only 1 million times dimmer than the sun. So it's a little bit easier to see if you were looking for it there. But the other thing you see in this spectrum is there's these wiggles, these little wiggles here. And these little wiggles have to do with oxygen in the atmosphere, water vapor in the atmosphere, carbon dioxide in the atmosphere. Okay. Now, it's not possible as of yet to directly, if we discover a planet orbiting another star, okay, and here's that star, and we have some evidence of a planet there, it's not possible at this point to take a spectrum of the light bouncing off that planet. Because the amount of energy or the amount of light that's bouncing off of it and coming at our telescopes is just incredibly faint, right? I showed you what the Earth looks like from Saturn. Now imagine trying to look at it from the distance of a star, of a distant star, much, 1,000 times farther away than that, 10,000 times farther away than that. It just becomes prohibitively difficult, even with the giant telescopes we have today. But we hope that within about 20 years, we'll actually have the technology to be able to do this kind of thing on real, planets with direct spectra of that reflected light off those planets. And so this technology, in principle, it's not impossible. It just was going to require work. And certainly within sort of a time span of your lifetime, we'll be able to do this kind of thing. Yeah?
Hover cars are possible, but they're not really doable.
Well, okay, so the question is, so the comment is, hover cars are possible, but we don't have hover cars all over the place, and they didn't happen. So is this going to happen? I think it depends on will, right? I think if there was actually a big driving need in the economy, if people really, really wanted to buy hovercrafts, right? If there's a huge market for hovercrafts as opposed to electric cars, right? Then maybe Elon Musk would have spent his time building hovercrafts instead of Teslas, right? But instead, there's probably a larger market for just electric cars that are really awesome like Teslas, and so they spend time building these, right? So I think it depends on what the drive is to do. There's a lot of people that think, that actually detecting evidence of life around another planet is kind of a big deal and is something we should try to do. So there is a fair amount of will to try to make this happen, and there are telescopes that are being built right now that might enable this to happen. It doesn't mean it will. It's like the hovercrafts or the jetpacks and all these things that people talked about. But this is, this is a little bit different. This is basically a measurement that could be done. But yeah, we don't know. It's hard to predict. It's impossible to predict the future. But it could be done. So rather than looking at the reflected light of a planet off a planet like this, the idea is instead to use the star itself as like a flashlight to shine through the atmospheres of these planets. Okay, and in the same way, if you remember last time I talked about how a lot of these planets have been discovered, you happen to be looking at a star in such a way that the orbits of its planets are edge on to us, so that when the planet crosses in front of the star, the overall luminosity of the star goes down a little bit, and you look for that dip in the overall luminosity of the star. But while this is happening, if you had a precise enough observation, what would also be going on is, when that planet is in front of the star, some of that starlight is going through the atmosphere of the planet. Okay? Like this. Here's the planet. The star is over here now. I've turned it to the side. The sunlight shining through the planet's atmosphere. And if there's molecules in this atmosphere, those molecules can absorb some of this light at preferential wavelengths. And those preferential wavelengths of absorption will tell us what the atmosphere is made of, what gases exist in the atmosphere. Okay? So here is just an example of what you could imagine something looking like all these little wiggles. So here's a background spectrum of stuff, and all these little wiggles are telling you about different kinds of molecules. Here's ozone, here's carbon dioxide, etc. So, this carbon dioxide line is pretty obvious. There's ozone. That would be very exciting to see. Now, Now, you might ask, does this actually work, and how can you get some practical way of thinking about this? One way we can get a sense of what the Earth would look like from afar if it were studied in this way is to look at something called Earthshine. Okay, so what is Earthshine? Earthshine is actually light from the Earth that then, the sun's light comes and hits the Earth. Some fraction of the sun's light that hits the Earth just gets bounced back into space, right? That's why the Earth is sort of visible at all from a distance. You've got the moon sitting there, right? And light from the Earth then, so light from the sun bounces off the Earth, and that light hits the moon and bounces off. And so we've done studies with spacecraft of looking at the light that bounces off the moon. That's called Earthshine. And in fact, when you look at the moon sometimes, right, you'll see there'll be a crescent moon, for example. But then there's a part of the moon you can still see even though it looks dark, right? So there's a part of the moon that's lit up by the sun, but then there's a part of the moon that looks dark, but you can still kind of see it sometimes, right? When it's real dark, you can sort of see it almost looks like a shadow of it. The reason why you can see it at all is that's actually light that's bouncing off the Earth and then reflecting off the moon. So you're getting a double bump. Okay. But the point is, you can look at this light that's bouncing off the Earth and then reflected back off the moon, and you can look at the spectrum of that light. And this is what it looks like. Okay. And what you're seeing there is you're seeing these clear signatures of different molecules in the Earth's atmosphere. So you're seeing, very clearly, for example, this is oxygen. And you're also seeing signs of vegetation. And you're even seeing signs of light scattering off the oceans. So if you know what you're looking at, it looks noisy to you because you're not, spectra are sort of notoriously hard to understand when you're just glancing at them. But, there are people who spend their lives trying to interpret exactly what these lines mean. And there's information there. And so you can extract information about the makeup of the planet by studying how and why light reflects off of it, what light gets absorbed in what way. Okay. So the specific lines that you can see, or the specific gases that you might find evidence for in the atmosphere of an exoplanet that might indicate the existence of life, those are called biomarkers. Okay. So biomarkers are spectral features that might indicate the chemistry of life. So the sort of out of equilibrium life, these biomarkers. Okay. O2 is the sort of the 20% of our atmosphere of our atmosphere that's oxygen, which is molecular oxygen, is a great biomarker. Okay. However, unfortunately, the features of O2, what it looks like in an absorption spectrum, are really easily confused with other things, unfortunately. So it's hard to dig that out of some data. But ozone, okay, which basically is a molecule that's created when sunlight shines on O2 and then recombines into this molecule O3, that's an excellent biomarker. It creates a really characteristic signature in a spectrum. So this is a spectrum again, how much light you measure at a specific wavelength. Okay, light is coming at some detector, you spread it through a prism, you figure out how much light's coming at every single wavelength, and so if you see a dip in the spectrum right around here, you have evidence for ozone, and that would be a really cool thing to see in the atmosphere of a distant planet. Okay. H2O, so water vapor, it's a little bit harder to see, but there's lots of different signatures on it. And if you saw that, it doesn't mean there's life, but you know that we're sort of following the water in this course anyway. And so seeing water vapor and ozone in the atmosphere of a distant planet would be a huge, huge deal, right? It would be very much looking like an Earth. And finally, methane is a byproduct of anaerobic life that we see on Earth as well. And so if you saw lots of these different features, here's methane in the Earth's spectrum, again, it would be a signature of this kind of thing. So this is generally what's meant by the word biomarker. Biomarkers are things we can look for in the spectra of distant planets that would be indicative of life existing on those planets. If these were ever detected, it would be a huge, huge deal. This would be a transformative thing. Okay? So just to give you a sense, this is what the spectrum of Venus looks like. The atmosphere of Venus looks like this. Again, this is the wavelength of the light. This is the brightness of the light. Okay? This is what the Earth looks like. Look at all this, how jiggity it is. And then there's Mars, right? Very flat, a big dip, and very flat. What is this big dip? That big dip is carbon dioxide. Okay? Carbon dioxide loves to absorb infrared light. That's why it's a big deal greenhouse gas. Okay? And even in the Earth spectrum, carbon dioxide is pretty present, even though there's not that much carbon dioxide, by mass, right? It just does a lot. But in Venus, there's a huge line of carbon dioxide because it's got a huge amount of carbon dioxide in the atmosphere, but nothing else, pretty much. Mars is the same thing. It's almost all carbon dioxide. Okay, so if you saw a distant planet that was in the habitable zone of a distant star, and you looked and you got all excited and you finally were able to measure its spectrum, and it looked like this, you'd say, wah, wah, it's probably more like Mars, right? So it's unlikely to have life. But if you took a spectrum of one of these things and it looked like this, and you saw ozone and water and all kinds of other stuff, you would get very excited, right? This looks like a planet that's alive. This looks like a planet that's a desert. Okay? So the point is, there's a lot of power in spectroscopy. These lines are very boring looking, but if you know what you're looking at, your imagination starts to run wild. Okay. Now, as I mentioned before, methane is another really cool biomarker. Okay. It produces strong absorption in the IR. And the important thing about methane is it's not super strong in the atmosphere today. Okay, but we think on the early Earth it was very, very important. Okay, remember the early Earth did not have oxygen on it. Okay, so if you were a distant alien civilization living 3 billion years ago, studying the Earth, you might say, wow, there's water vapor on this planet, but there's no oxygen. Because there wasn't, but there was life. So how would you detect that life? And so it turns out that methane might be a very important biomarker for that kind of early life. Okay. The other thing you can learn about the spectrum of a planet is actually whether or not it has plants on it. Okay, whether or not there's a forested planet. Because you can see that directly in the spectrum of the Earth. So for example, plants reflect infrared light. Okay? So you think of plants as green, and they are, okay? But if you could see in the infrared, they're actually reflecting way more infrared light than they are that green visible light. And you can see that in this picture here. This is the reflectance of plants, basically, as a function of their wavelength. And you can see that there's a bump right here. This is green. So it's reflecting mostly in the green. That's the chlorophyll bump. That's chlorophyll is absorbing the red light and the blue light, using that for photosynthesis and spitting back out or reflecting back out the green light. That's what this bump is. But then there's a huge bump, a huge edge in the spectrum that's coming from reflected infrared light. So if you were to see this kind of feature in the spectrum of a planet, okay, without actually even being able to take an image of the thing, this would be indicative of, for example, maybe a forest around this planet or covering this planet. Okay. The other thing you could think about doing is watching a planet and seeing whether or not its overall brightness and reflected light changed as it orbited its parent star. Because that's what the Earth does. Its reflectance changes over the seasons. That's because ice is very reflectant. So if you build up a lot of ice on your planet, the sunlight coming in is reflected back off that ice. But then in the summertime, the ice goes away and the reflectance of the planet goes down. And so if you were to see over time, a planet that was going through seasonal cycles, you would see it get brighter and dimmer just because its reflected light would do that. Okay. So again, these are the kinds of things you could look for to get a sense of what's going on the surfaces of these planets. Okay. So, just to sort of wrap up here about talking about this. So there's real hope, and sort of in a very practical sense, that we're going to be able to go out and characterize planets that are orbiting other stars. We've found them. Okay, we're to the point now where we're finding these planets, and we're going to find more. So a couple missions are going to launch over the next 5 years that will discover even more of these things. And instruments and telescopes are being constructed right now that will be able to go out and measure we hope be able to go out and measure the spectra of the atmospheres of these planets and begin to look and see whether or not they actually have indications in their atmospheres that they're alive, that they're planets that have life on them. Okay? We know they're there. We know they live at distances from their stars where they could have liquid water. The next step is to go out and actually look for the biomarkers. If you found evidence for these biomarkers, right, and you found that it was common, it has pretty profound implications for our future in this, in this galaxy. Because you have to go back and think about things in terms of the Fermi paradox, right? One of the questions we ask ourselves is intelligent life common in the galaxy? One of the first ingredients is how common is basic life? Because we think you have to have the basic life first, then the intelligent life happens. If we were to go out and discover that basic life, simple life, was flush throughout the galaxy, that drastically increases the chances that you're going to have then intelligent life that evolves on those planets. But if that's the case, you start getting a little nervous about the eerie silence. Because if you've got 50 billion, or even 1 billion planets in the galaxy that at some point in their histories have evolved intelligent species, most of them have had more than 1 billion year head start on us, and there's no evidence that they're there. So does this mean that the lifetime of intelligent civilizations is short for some reason? Or does it mean going from that simple life to that intelligent life is really, really hard or unusual? So there are profound implications just for a bump in a spectrum. It looks, it might not seem that exciting. But if you think about the implications of potentially seeing some lines on a piece of paper that look like this, as discovered, say, 15 years from now, they could be profound about how we see ourselves, as a civilization, as a species. The next question, of course, and the thing that gets people very excited when we're talking about searching for life, is not necessarily looking for microbes, right? Some people like microbes, some people like plants. But what would be really amazing is if we discovered some other kind of life form that we could have a conversation with, okay? That we regarded as intelligent, that could teach us something, or that we could teach them. Like a real galactic cousin that was sort of a peer in some way. Or perhaps that would dwarf us, most likely, in terms of what this civilization understood about the universe. Okay. So how do we go about doing that? One approach for searching for this intelligent life is to start by searching for their likely homes, and that's kind of what we've been doing, right? So we've been discovering exoEarths, and we've done that. Okay, that's actually happened. The next step we're going to do is we're going to look for biomarkers in the spectra. We're going to look for all of these fancy different things in the spectrum of these planets, and maybe we'll see, aha, that planet is alive. So then we might think, boy, that would be an interesting place to look for, ET. But, there's another way of thinking about it, is to assume that intelligent life is common, and then to go out looking for it, trying to see if there's evidence for that somehow. Okay? Now, if you assume, this is a big assumption, but if you assume that these civilizations are sort of like us in that they would have some desire to communicate, And you assume that they're sufficiently advanced that sending signals throughout the galaxy, searching for messages in bottles, basically, is not prohibitively expensive for these civilizations, then we can go start looking for them. So the point is, this approach is, let's skip over the hard stuff about trying to find planets and measure their atmospheres and figuring out whether there's biomarkers or not. Let's just go out and point our telescopes places where there are stars and see whether or not something interesting is emanating from those locations. Like maybe there are signals that are coming from them. Maybe they're just trying to communicate with us. Okay? Now, what if you don't find anything? I'll preface this. What does that mean? Well, we don't know exactly what it means, right? Does that mean there's no life, there's no intelligence, maybe they don't have technology, maybe our methods are flawed, or maybe they just don't want to talk to us? But a lot of people believe that it's worth looking because if you actually found something, it would be sort of a big deal. Okay? Now, what's interesting, right, is if you look at Earthshine in the radio band, you see pretty strong evidence that there's nothing natural going on there. Okay? There's a huge bump in the radio emission from the Earth that does not look natural, and it peaks right around 100 megahertz, and that's right around the FM band. Okay? So there's FM radio signals just streaming off the Earth. And if you knew what you were looking for, you would see this. It looks kind of crazy. There's this huge, huge bump. Okay? So that's just one example that there's stuff coming off the Earth right now that betrays our existence. Okay? You would even see it change as it spins. Okay? So you see, for example, the radio intensity coming from the Earth change as TV and FM transmitters sort of orbit around. Okay? And so you'll see, big bumps as different parts of the world come into view and then go out of view. So this kind of idea motivates a program that's called SETI. It's the Search for Extraterrestrial Intelligence. And the idea of SETI is you're searching for artificial radio signals, so not natural radio signals, but artificial radio signals that might be coming from intelligent life. And underlying this is the idea that it's probably intentional, but perhaps not. Okay? One of the motivating factors of this, right, is the stars are really far away. Does anyone remember the typical distance between stars around the sun?
5 light years.
Good, really good. I said 6 in lecture, but I'll take 5 is great. About 5 light years is a great answer. Keep that in mind for Tuesday. Just a hint. So that's a long way, okay? And if 1 in 100 stars has life, that becomes a really long way. So it takes a long time to travel between stars that are that far away. And it's also expensive, and you got to worry about people dying along the way. But if you're just sending signals, that's cheap. Okay, it's easy to send a radio signal just off in any direction rather than sending a whole spaceship there, right? Okay. Now, if you're going to do this, what kind of light would you use? Well, the thing that's been decided on, and again, it's not completely clear, but microwaves appear to be sort of an interesting thing to think about for sending these signals. Okay. So, microwaves are usually measured in the megahertz. Remember, this is just the frequency of the light. It's the same thing as wavelength. It's just you can refer to light as a frequency or a wavelength, and in sort of radio bands, long wavelength bands, you tend to refer to the frequency. And the frequency of microwaves is around 1,000 to 10,000 megahertz, and it's within this range that it seems to make sense to be sending signals. The reason why is that there's not a lot of cosmic background. There's not a lot of sources out there in space that are producing a lot of signal in this microwave range, and so if you want to do some artificial communication, you would pick that range. Okay. Another thing people have thought about is lasers. Lasers are very distinctively made by some intelligence because they basically are a single wavelength. Okay, so this laser pointer is green light, period. Like at a very, very sharp wavelength, it's green. So this is not a natural thing. Okay, you have to work pretty hard to make a laser. Whereas if you just take a rock and make it hot enough, it'll glow like a light bulb does. But making a light, so some natural process can make things glow with the black body radiation, but making a laser is hard. And so the idea is you could use lasers as communicating signals because they'd be very sharp spikes in wavelength, so that doesn't look natural either. Okay, whoops. I'm going to focus on radio for now. So our galaxy is full of radio emission, it turns out. But it's just not as bright as it is in other emitting in other kinds of bands. Okay, this is a picture of our galaxy, all sky of our galaxy at a radio frequency, and so it's shining there. But if you're very careful and you look at how the emission from the sky changes as a function of the frequency of the radio emission you're just looking at, right? Imagine you're just looking out in the sky and you're just measuring how much stuff is coming at us at all different wavelengths. There's a lot of stuff coming out around 0.1 gigahertz, okay? And then it kind of dips down, and there's a spot where it's low, and then it kicks back up again right above 10 gigahertz, okay? So here this is water emission and oxygen emission, so there's all this stuff in here. But there's this sort of spot in the middle between about 1 and 10 gigahertz, and more precisely it's more narrow than that, where the background is low. So the light's not very bright coming from space in that specific wavelength range. And specifically, it sits right between an emission line of hydrogen and hydroxyl. And so people call it the water hole. Okay? And so there came to be this sort of discussion of, if you've got, imagine you had an intergalactic set of, multiple advanced civilizations throughout the galaxy, and they're sending signals to each other, right? In much the same way, we have to figure out what waveband we're going to communicate in with a walkie-talkie or with the cell phone, right? Your cell phones have very specific wavebands that they use to communicate with. This intergalactic civilization has decided, look, we're going to communicate with this waveband because there's not much natural noise there. Okay? The way the cell phone companies have sorted out the wavebands they're using is there's no noise from TV and there's no noise from other things there, right? They've picked a waveband that's reasonably quiet. You can imagine the aliens thinking along these lines, except their background noise is just natural stuff. So there's this sort of quiet, what's called the water hole. And the idea is, of course, that like these civilizations are gathering around the watering hole to send their signals across. Okay. Do people understand why it's called the water hole? H2O. Okay. So questions about this? Now look, we're just making stuff up here, right? The SETI people are fundamentally just making stuff up. They're just saying, if we were an advanced alien civilization, what would we do? We'd probably try to pick a wavelength band like this. And so that's where they started looking. It's a total shot in the dark, but that's what they're doing. Okay? There's basically two strategies. These are just two leaders of the sort of SETI endeavor. Jill Tarter is the director of the SETI Institute now. Frank Drake is one of the sort of classic guys who's worked on this problem. The Drake equation guy has worked on this for a while. Just put some faces up there. There's basically two strategies that people use for thinking about how to do this, for how they're going to pull this off. One is a targeted survey, and so the idea is that you have some facility of radio telescopes, and you say, this planet, this particular star system is really interesting, because, for example, maybe we know there's a planet there, and we're going to stare at that star system and look for funky-looking signals coming from it. The other idea is to do something that's called piggybacking. And so the idea behind that is you've got astronomers using radio telescopes to do their science. Okay, they want to do some specific science that's not as sort of loopy as looking for aliens, right? And so you go out and you're trying to study something with a radio telescope, but you're pointing in that part of the sky anyway. And so you go ahead and use that pointing to sort of look for signals too. So there's sort of two strategies there. Just to throw up a couple examples, there's something called the Allen Telescope Array. It's called the Allen Telescope because it was funded by Paul Allen, the sort of billionaire from Microsoft fame, has donated a lot of money because he's interested in this kind of stuff. The idea is it's an array of telescopes that are, and this idea is it's a targeted survey. They're looking at specific things, and they want to go out and see if they can see evidence of this, of some alien civilization that way. There's another example of something that's piggyback. It's called SERENDIP, the search for extraterrestrial radio emissions from nearby developed intelligent populations. This is operated out of Berkeley and Cornell. And what they're doing is they're doing piggyback studies using the Arecibo Observatory in Puerto Rico. This is one of these giant radio telescopes. And so they're doing this too. This is the program that operates what's called SETI at home. I don't know if anyone's ever heard of SETI at home. Has anyone heard of that? A couple people. This is a thing where you can basically download a screensaver to your computer, or effectively it runs in the background on your home computer when you're not using it. And it uses the CPUs of your computer to search for alien signals. So it's harnessing sort of the compute power of just like general citizens to hunt through these data and try to find a signature of that. So if you think this stuff is cool, you can download that and put that on your computer. They're doing a lot, well, they're going to do a lot less with your personal information than, say, Facebook is. So I wouldn't, I wouldn't worry about it. What are they looking for? Okay, they're looking for signals that look artificial. Okay, so the idea is that you're looking for things, and generally what's just thought of as a very sharp peak of emission at a very specific wavelength range or a frequency range. Okay. So this is called narrowband in radio, so you might think of having a narrowband signal. So you're looking for a signal that's in some radio emission that's very tightly clustered right at a specific wavelength. And again, it's analogous to the laser pointer, right, which is light at a very specific wavelength of green, not a general white light. You're doing that, but it's in the radio. Okay. The other thing you want to look for, or what people think they want to look for, is pulsed signals. So you think about Morse code. Okay, a series of zeros and one, like boop, on off kind of communication. The idea here is that we would believe that this idea of the base of communication being zeros and ones is something that an alien civilization would comprehend and would use. It's sort of the simplest way of sending a signal. So if you think about basically what underlies computer technology, the sort of general binary way of thinking about numbers and thinking about counting, that is probably the most basic system that you would try to communicate with another civilization with, right? Because when they're going to talk about numbers, right, they're not going to use base 10, right? The reason why we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we change it to a 1, 1, and then we go 21, 31, etc., is because we have 10 fingers, right? So that's a very, biased thing to assume that all civilizations would have a base 10. There's no reason to have a base 10. In fact, other civilizations on Earth have used different base number systems. So you probably go to binary, and so that's sort of what you're thinking. So we would expect artificial signals to have very narrow bandwidths. You're supposed to be thinking about Morse code here, and but unfortunately, so far, we haven't found anything. That's the upshot. If we had found something, you would know about it. And so people haven't found anything yet, and they keep looking. There have been a number of kind of fun, interesting false alarms that people have discovered, where they see something that looks 100% artificial, and they go back the next night and look at the same spot, and it's not there. And so in most cases, people think that they were just some satellite that they lost track of, and we were just seeing a satellite beacon or something. But there have been a couple, there's one really famous example of they saw something and they called up all these people, and they were going to get ready to have some kind of mini press release, and then the signal went away. So that's kind of where people are now. And most people think, if you had to poll people, most people would bet you're not going to find anything this way. But it's cool to look. People feel compelled that you have to look, because if you did find something, it would be so profound. Okay. But to keep in mind, right, an alien civilization does not necessarily have to be sending us signals on purpose. They could just be, going about what they do in broadcasting signals, and we could be looking for those, right? And so in fact, we are doing that, right? We are already broadcasting signals to the stars. Because we, as we already discussed, have this big FM footprint. We're also broadcasting TV signals very powerfully out into space, right? So, for example, people living in Alpha Centauri, if there were alien civilizations there, they would just be catching up to sort of the first season of The Walking Dead now. Okay? Now, people over here in 51 Pegasi would be seeing TV broadcasts from the 60s just now. Okay, so they would be discovering the Beatles. Beatlemania is just starting to happen in 51 Pegasi right now. Okay, yeah.
Are we actually sending the TV shows?
Well, the TV broadcasts are escaping the Earth's atmosphere and going out. So yes, I mean they would be able to see those TV shows. I mean if they were sufficiently advanced, right, they would see these artificial signals emanating from the sun, and they could probably decipher them. They're significantly advanced enough, right? So yeah, I mean, some level we are. I mean, we're sending them information. It's unclear what they would make of this, but they could decipher it, in principle, if they were intelligent. We know there's this, by the way, 51 Pegasi is the first star with where a planet was detected. We know there's a planet here. Okay. One of the first really powerful broadcasts was the Berlin Summer Olympics in 1936. So this would be sort of the first signal that the Earth broadcast into space. This was sort of like, we're here. Our "we're here" announcement that would then be propagating out into space, right? So this was the one where Jesse Owens won 4 gold medals in front of Hitler. So it's sort of an interesting one to, and this guy's doing a Heil Hitler. I mean, it's crazy, right? In 1939, not too long after that, FDR did the first TV broadcast from a US president. Okay, so this was sort of the era where things were being first broadcast. So that was about 70 or 80 light years away or so. I think I did the math slightly wrong, but 80 light years away. And so that's where we are. Okay, so stars within this sphere would be getting signals from us now. Okay? And so, this is sort of supposed to give you a sense of, stars way out here would then be seeing our sort of radio or TV broadcast during World War II. Stars within here are now seeing the sort of Janet Jackson Super Bowl show, right? So that's sort of that's what we're doing. And we're doing this, right? We're not blocking these signals. So if you're worried about alien civilizations discovering that we're here, well, they already know we're here at some level if they're watching. So this is where we are. Okay, and so, but another thing to think about is if there was some advanced civilization here that's just getting our Jesse Owens thing now, they would send a signal back, but it would take 80 years to get back to us, even if they wanted to communicate with us, right? So, these are sort of the realities that you have to think about. So, it's not most of the galaxy, but we're getting to a point where it's a reasonable chunk. So not only can we look for signals from other stars, but other civilizations that are out there might be looking at signals from us. Now, you might think, well, geez, the fact that we're not detecting a lot of external TV broadcasts or radio broadcasts coming from other civilizations might be telling us that the galaxy is sort of without a lot of this other intelligent life. But, the whole deal with TV is it's kind of a dumb way of communicating a general piece of information, in the sense that it's a hugely wasteful way of transmitting a signal. Because what you're doing is you're taking a signal, right, and rather than just sending you the information directly, you're just broadcasting it in all directions. And so the strength of that signal falls off like 1 over the distance squared, because most of the information you're spitting out is not going to a TV antenna. Most of it's just like going out into space. Okay, and in fact, if you look at the rate of TV transmission power, while it's still growing, okay, it's been growing over the last, certainly since the beginning, it started growing a lot. That's starting to dip down now because people have cable. Okay, you have direct, people are not using TV broadcasts anymore. Using this more direct kind of way of transmitting information. So you might imagine, right, in 1,000 years or even in 100 years, maybe even in 20 years, we're going to go pretty much radio silent, maybe. And so there might only be this very brief period of time where civilizations, oh wow, we figured out how to make radios. And then at some point they're like, well, this is stupid. And then they stop doing it. And they start doing something more efficient. And so that might be why the galaxy is quiet in the radio, that there might be even more sophisticated ways of communicating that we just haven't encountered or developed yet. Okay. Yeah?
Are there any theories on how to, on those ways to communicate, maybe that are, broadcasted at a faster speed than the speed of light?
Yeah, not really. So yeah, the question was, are there any theories or ideas about how you might broadcast at a faster speed or communicate at a speed that's faster than the speed of light? That is a fundamental no-no in as far as we understand in basic physics. So sending a signal to someone else at a speed that's faster than the speed of light is effectively forbidden by special relativity, by the theory of special relativity. So things start to go haywire if you can start communicating faster than the speed of light. There's a lot of logical inconsistencies, etc. The only way that you could consider doing something like that is you have to significantly warp space-time in such a way. So what you can't do, so let me be very precise about this, what you cannot do is travel through space or send a signal through space faster than the speed of light. So there's a lot of reasons why we think that you just can't do that. What you could imagine happening in some crazy scenario is you actually warped space enough such that you could travel through this warped space in such a way that you could get from one place to another in what seems at a very almost instantaneous speed, but it really has to do with the warpages of space, of actually changing space-time. And so when people talk about like wormholes, that's what the idea of a wormhole. If you saw the movie Interstellar, like that was part of the idea with Interstellar, is that there's sort of a strong warpage of space and it really changes your perception of time and this kind of thing. But broadly speaking, the answer is no. But you could imagine trying to communicate with things other than light. So neutrinos are one possibility. So neutrinos are an interesting particle because they travel sort of through things easily without interacting with them. And these days, the cutting edge experiments struggle to detect them and just count them and figure out what their energies are, much less build a spectrum out of them or use them to send signals. But you could imagine, in 1,000 years, we really understand neutrino physics very well. We figure out ways of sort of subtly detecting neutrinos, and maybe neutrinos become the information carrier of some advanced civilization. So, I'm just throwing that out there. There could be lots of things that eventually could happen if the civilization is sufficiently advanced that we're just not even thinking about. It's like this might, using radio waves might be equivalent to like sending smoke signals. It's like it made a lot of sense. Okay, it was a super clever way to sort of send ideas back and forth over long distances before you had radios. But once you invented radios, you realized, well, we shouldn't do this anymore. We should do something else. Or maybe like the telegraph or something. You know what I mean? Like, so there could be some just sort of technological advance that we haven't discovered yet that you could imagine advanced civilization using. Okay, we're sort of grasping at straws at some level to figure out what we should even be looking for. We've actually sent a message out to a nearby star system. Sort of a more, rather than just accidental TV, we've actually sent a beamed message where we've tried to sort of be more careful about what we're doing. It was called the Arecibo Message, and it was sent in 1974. It was a digital pictogram that had 1,679 bits of information, so a teeny tiny bit of information. And the amount of bits was the product of two prime numbers, so the idea was this would mean something to them, right? It's an advanced civilization, they'll understand math, they'll understand what prime numbers are, so it's this kind of thing. And it was actually beamed towards a star cluster called M13. So what was sent was a bunch of binary numbers. The basic number system we use, sort of like we're a base 10 system people. I don't know why that was decided. The basic elements for life. So we tried to encode, hydrogen, carbon, nitrogen, oxygen, phosphorus. So these are the elements that we rely on for life. Okay. And does anyone know what these numbers correspond to? Like, why does this mean carbon and this mean hydrogen? Sorry, say it again. Yeah, right. It's the number of protons. It's the thing that tells you what the element is, the number of protons. Right, exactly. Good. And then even the population of the Earth at the time it was sent. So, however, it was beamed towards this star cluster, which is 25,000 light years away. So we're not going to get an answer for another 50,000 years. But, that's where we sent it. It was more symbolic, right? So the idea with a lot of this stuff is it's sort of symbolic. It's much like it really is a lot like putting a message in a bottle. Okay? You put a message in a bottle and you throw it out in the ocean, you're not really expecting an answer. Okay? But it's this sort of, poetry of it all, right? So something that's even probably more, romantic than that were these plaques and records that were placed on the Pioneer spacecraft and the Voyager spacecraft in the 70s. Okay, they were actually physical artifacts that we put there to sort of describe to some, unnamed entity, like who we are and what we're all about, right? So this is sort of a couple of humans here. This is supposed to be a pictogram of we're the third planet from the sun. Okay. Here's the spacecraft that we've launched. It's just a very sort of simple sort of etching of what's going on here. There are these Voyager records. So yes, records. So like outdated technology even for us now, basically. The records are really cool though because they've encoded a bunch of images. So 115 images of different things about the Earth. So you ask yourself, if you were going to send some token to some alien civilization, like what would you send them to teach them about what we're about? What are we about as a civilization? Like what makes us us? Okay. Encoded in this record were a bunch of sounds, like natural sounds of like surf, wind, thunder, birds, whale sounds, other animals, a bunch of different music from cultures and eras throughout the Earth, the spoken greetings from 55 languages on Earth. There was a printed message from Jimmy Carter, who was the president of the United States at the time, and the UN General Secretary. And just to keep this in mind, so we sent this off, it'll be 40,000 years before this thing gets close to another star system. So it really is just sort of let it go. It's probably not going to be discovered by anything, but it's more like a gesture of what we might, want to communicate. Okay. So this is a quote from Carl Sagan, and Carl Sagan was a famous science communicator who was sort of very popular in the 70s and 80s. If you've never heard of him, he's definitely worth checking out. If you like this kind of stuff, you can find like all the original Cosmos shows on TV. There was a reboot of Cosmos by Neil deGrasse Tyson that happened last year, which was excellent. But Carl Sagan was the person who sort of did it first and did it in a sort of different way. It was definitely more of like a 70s, 80s kind of style to the thing, but it's kind of charming. It's worth checking out. I want to sort of close actually with a quote from Carl Sagan that has to do with this picture right here. So this is a picture of the Earth taken by the Voyager 1 spacecraft. And this picture of Earth was the first one that was really a distant image of our home planet that was taken from the outer solar system. Okay, so this was the first time that humans had sort of been able to look back and see the Earth not as this glorious giant blue thing that we sort of saw from the moon, but actually an even smaller, distant, pale thing, this little dot right here, as imaged in the year 1990 on Valentine's Day. This became known as the pale blue dot. Okay, so it sort of evokes the fragility of our planet in the grand scheme of things, right? So the quote, so Carl Sagan has a pretty famous quote about this. So he wrote a book called The Pale Blue Dot that was sort of inspired by this image. And I've got a quote from it here. I'll read just part of it. So what Voyager did is its science mission was basically over. It had gone out to sort of explore the outer planets, and that part was done. And so what the engineers decided to do is just turn the camera back home and take this snapshot. And what was amazing about this image is that it was so boring, right? It was spectacularly plain. You can hardly even see it. So the quote is, from this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider that dot again. On it, everyone you love, everyone you know, everyone you've ever heard of lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every supreme leader, every saint and every sinner in the history of our species has lived there, on a mote of dust suspended on a sunbeam. The power in this image, right, is that sometimes we get very caught up in self-importance. Not just our own importance as individuals, but the importance of sort of the trappings of what are around us. Like what's important and what's not, what it means to be the most popular person in the room, okay, the richest person alive, the most powerful person alive, some kind of supreme leader, as he says. But in a cosmic scheme of things, right, the most powerful supreme leader of all on Earth has some kind of this thing going on, right? It's just this tiny thing. So what does it mean to be on this dot and then to look out and think about these things? The thing about this course that I hope has, inspired a little bit of thought in this direction is that when we look out into the stars at night, we are seeing possibilities for billions of other pale blue dots, right? And then so on each of those pale blue dots, right, there could potentially be entire civilizations filled with things that love each other, right? That live out their lives, that have ideologies and economic doctrines and their own religions. Are there universal truths that everyone agrees upon? Are there not? Now, we don't know the answers to these questions, but the possibilities of these are very real. And there's power to think about that context, right? Even if those other civilizations aren't there, it's useful to think of our own in that broader context, I think. Okay? So if you don't remember anything else from this course, think about that kind of really big picture and see if you can use that in some way to sort of maybe help you, shape your own priorities. Okay? All right. Thanks very much, and good luck on the final.